Hi there. This video is going to look at something called geometric proof, which is a concept to do with using our knowledge of angle rules in order to prove a statement that's been given. Let's have a look at this first example here. This example is from mathscentre.co.nz, which is a website that has sort of online booklets. So if you want to practice more of these examples, you could go to that site. So if we look at this diagram here, the information we're given is that line KM is an axis of symmetry. So that means everything on one side of that axis is exactly the same on the other side. So angles, lengths of lines are all equivalent on either side of that axis. We also know that the length of QN, which is this length here, is equal to the length of QK and also the length of QL. So we've got a couple of isosceles triangles there that we could perhaps use. We are also given this angle, so 120 degrees, and this angle here, 30 degrees. So immediately I can see that this angle here is going to be 30 and that angle there is going to be 120. So I'm just going to pop those in as a reference. Now what we need to prove is that KLMN is a cyclic quadrilateral, and we need to recall our knowledge of cyclic quadrilaterals, and one of the rules that we should know is that opposite interior angles of a cyclic quadrilateral add to 180. So because I've already found one interior angle here, so 30 plus 30 is 60, then I think I'm going to use this rule here. Okay, so the one we've just come up with. If we can prove that this angle plus this angle here add to 180, then we will have proved that KLMN is indeed cyclic. So how are we going to work out what this angle is? We somehow need to use these angles around Q. So we've already found out what this angle is, so let's start our proof. That angle there is LQM, so angle LQM is equal to 120 degrees by virtue of the axis of symmetry. And then we could probably work out this one here because we have angles at a point. So angles at a point add up to 360, so we can work out LQN. So angle LQN is also equal to 120. Okay, so 120 plus 120 is 240. So 360 minus 240 gives us 120. And the reason is angles at a point. Angles at point. We're going to use the virtue of these isosceles triangles here now, as well as this axis of symmetry. So this angle here is 120 degrees, which means each of these individual angles are 60. Okay, by virtue of that axis of symmetry. So if we just include those two angles in our proof here, so LQK is equal to angle KQN, which is, both of those are 60 degrees each, and that is by virtue of the axis of symmetry. So if we look at, say, this triangle here, triangle KQN, that triangle is isosceles. Okay, we're given that information here, which means if this angle is 60, then this angle here plus this angle here must be 180 minus 60. So it turns out that because this is an isosceles triangle here, those two angles must be 60 as well. So angle NKQ is equal to this angle here, so KNQ, and both those angles are equal to 60 degrees, and that's due to base angles in isosceles triangle. So now that we know what this angle is, which is 60, this angle here must also be 60 because of that axis of symmetry. So angle LKQ is equal to 60 degrees, and that's axis of sim. So now that we've found this angle here, if we add that angle up, so 60 plus 60 is 120, this angle here must be 60 degrees, and indeed it is. So what we've found is that angle LKN is equal to 120 degrees, and this means that angle LKN plus angle LMN is indeed equal to 180 degrees. Therefore, we can say that KLMN is a cyclic quadrilateral. Okay, let's have a look at another example. So this example here is taken from the website nzqa.govt.nz, and it is a question from a past exam from 2012. So this question is an excellence question, and the questions to do with proving statements given generally are excellence questions. Okay, so this example gives us, well, we're told that we've got a couple of isosceles triangles here. So triangle JKL, so JKL is isosceles, as well as triangle LMN, also isosceles. So can we prove that JK is parallel to NM? What we are also given is that we're given this angle here labelled as X. So somehow we need to use X in our proof. Let's have a look at this isosceles triangle, JKL. So what we can say is because that triangle is isosceles, then that angle there will also be X. So to start our proof, angle JKL is equal to X due to base angles in isosceles triangle, which means we can work out this angle here by virtue of interior angles inside a triangle add to 180. So that angle there is angle JLK. Just take care when you're naming your angles that you're using the letters in the correct order. So JLK is equal to 180 minus that x minus that x, so which is minus 2x. And that's angles in triangle, add to 180. This angle here is vertically opposite this angle. So vertically opposite angles are equal. Angle MLN is also equal to 180 minus 2x, and that's vertically opposite angles. Vertically opposite angles. So we're on to our second isosceles triangle. So these two angles must be the same. So those two angles there plus this angle here must equal 180. So what we can say is maybe just work out one of these angles. So 180 minus this angle here, then divided by 2 will give us that angle there. So that angle there, the one that we're that I've asterisked, is angle LNM. LMN is equal to 180 minus, I'm just going to use brackets here, minus this angle, which was this one here. So minus that angle and divided by 2. So we're just finding one of those single base angles there. So we just need to simplify a wee bit. 180 minus 180 is 0. Actually, if we just rewrite that top line like this, 180 minus 180, then we've got minus 2x, which is plus 2x. That's all over 2. So 180 minus 180 is 0. We just leave a 2x on the top, divided by 2, which is just x. So angle LMN is equal to x, which is this angle here, which means that this angle here must also be x because they are base angles in an isosceles triangle. I just need to put a reason here. This was angles in a triangle and base angles in isosceles triangle. So what we can see here now is that these two angles are both x, these two angles are both x, so we can see we've got some, if I just look at this angle here and this angle, they are on alternate sides of line KN. They are exactly the same, and we've got two lines going through here, JK and NM. So it looks like we've got alternate angles here. Alternate angles are equal, therefore JK must be parallel to NM. So if we just finish off our proof here, what we can say is angle JKL is equal to angle LNM, and we can say that those two angles are alternate angles on parallel lines. Therefore, line JK is parallel to line NM.